Hello and welcome to the session. In this session we'll discuss about logistic regression. So what is logistic regression? So basically linear regression we have seen in the previous sessions, where we use linear regression to predict the numerical responses, but linear regressions were not suitable for predicting categorical values, right? So logistic regression, though the word itself says it's regression, it is still very much suitable for binary classification problems. So logistic regression, though it is a regression model, it is suited for classification problem and very much for the binary classification problem, and it is most suited when the output is categorical. So in the sense, let's see this example. If you have to classify between a mail whether it is a spam or a not, or you can the categorical dependent variable in this case would be a binary response saying yes or no. Or the second example, where I want to decide whether the student should be admitted or not based upon his entrance examination marks. So categorical variable response in this case would be admitted or not admitted. The third case, whether student being pass or fail based upon the marks secured. So the categorical variable response would be pass or fail. So in such cases, it's good to go for logistic regression. So logistic regression is basically a supervised machine learning algorithm. Though the word says regression, it is largely used for classification task, where the goal is to predict the probability that an instance belongs to a given class or not. So you need to remember this. Here the goal is to predict the probability for an instance. So we are going to see this next, how we can find the probability that the instance or the test variable will belong to the class or not. So logistic regression is widely used for binary classification, where we use a sigmoid function. So we'll be using sigmoid function here to represent the relationship between the dependent variables and the independent variables, and it will produce a probability value between the 0 and 1. So these are the keywords need to be remembered for logistic regression. It is though it is a regression model, it is used for binary classification. It uses sigmoid function, and it is having the prediction is based upon the probability value, where the value will be between 0 and 1. So we will see that in logistic regression, instead of fitting a regression line, we will not have a regression line we saw in linear regression or in multiple linear regression models in the earlier videos, where we had a linear relationship between the independent variables and the dependent variables. Now in logistic regression, we will have a S-shaped curve. S-shaped curve which represents relationship between the independent variables x and the dependent variables y, and it will predict the values either between 0 and 1. This you need to remember. The output will range between 0 and 1. So let's see how logistic regression works. So basically a logistic regression model transforms the linear regression function continuous value into a categorical value using a sigmoid function, which maps any real value set of independent variables to a value between 0 and 1. So let's say I have x value as 1, 2, 3, 4, 5, 6 up to 10. But in logistic regression, we are going to convert these values of x from 1 to up to 10 and map it to a value between 0 and 1 only. Okay, so this is the relationship, S-shaped relationship, which we have in logistic regression. Okay, so you can see here that the value of this S-shaped curve ranges between 0 and 1. This is 0 and here you have 1. So the relationship in a logistic relation between the dependent variables and independent variable is represented by this S-shaped curve, or we also call it as a sigmoid curve, where the value ranges between this is 0 and this is 1, and exactly this is the where, right, it has a positive and this is the negative part of x, and exactly at 0.5 the curve will change. So greater than 0.5 the values will be on the right hand side of the curve, and less than 0.5 the curve will be on the negative side of the x-axis. This is known as the logistic function, and the equation for the logistic function is 1 divided by 1 plus e power of minus z. So let's see the math behind this. Let's say I have some independent input feature. So these x is my input features which are independent, right? So I have a matrix of features, and let's say y is my output, which is a dependent variable, and y can only have values between 0 and 1. So if I say y is 0, it belongs to class 1. If I say y is equal to 1, it belongs to class 2. Now let's say I apply the multilinear function to this input variable x. So if I apply the multilinear function to this variable x, this is how I apply. Because it's a linear function and it is multiple, it is summation of wi xi. It's like basically like writing w1 x1 plus w2 x2 plus w3 x3. So basically I have many independent variables, right? x1 x2 or x3 like that. So you just sum it up, right? So instead of that, you just sum it up using the summation or the sigma I is equal to 1 to n wi xi plus b. So this is our multilinear function for the independent variable x. So xi is basically the xi values or the observations of x, and w are nothing but the weights or the coefficients, and b is the bias term, also known as intercept. So simply this can be represented as dot product. So basically wi into xi, basically it's a dot product between the weight and the coefficients and the x values. So this is very similar to what we have seen in linear regression, right? Especially in multiple linear regression, this equation is similar to what we saw in multiple linear regression methods. So let's now use the sigmoid function, right, where the input is z and we find the probability between 0 and 1, that is the predicted y. So input is z and the probability is the value should range between 0 and 1. So this is t and this is sigma value. As I told you, sigma of t is nothing but 1 by 1 plus e power of minus t, or instead of t if you write z, this would be z, the x-axis would be z, the y-axis would be sigma of z. Okay, and sigma of z is 1 by 1 plus e power of minus z. So remember, z is the x-axis, sigma of z is the y-axis. So as shown in the figure here, the sigmoid function is converting the variable data into a probability. That is what you have to note, right? The sigmoid function is converting the continuous variable data into a probability between 0 to 1. So how do you convert it into probability is, if sigma of z, this one, the y-axis, it tends towards 0, it tends towards 1 as z tends to infinity. You can see this in this figure, right? Sigma of z is nothing but this red line, right? So sigma of z, it will go to 1, this is 1, as z, that is the x-axis, is going to infinity. Similarly, sigma of z tends to 0, here this one, as z tends towards minus infinity. That means I'm now talking about the negative axis. And what you have to remember is sigma of z is always bounded between 0 and 1. This is 0, this is 1. Okay, so the value of this sigmoid function or sigma of z is always between 0, this is 1. So how do you write this in terms of probability is, probability of y is equal to 1 when you have sigma of z, and probability of y is equal to 0 when it is 1 minus sigma of z. Okay, so this is how you write the probability. The probability that it belongs to class 1 is sigma of z. The probability that it belongs to class 0 is 1 minus sigma of z. And what is sigma of z? Nothing but 1 by 1 plus e power of minus z. So let's now look into the equations of logistic regression. So if the probability is predicted via the linear regression, so this is our linear regression model where p of x is equal to a0 plus a1x. So we know that linear regression will generate values from minus infinity to plus infinity. Now we have to map this, right? We have to map minus infinity to plus infinity to the probability range of 0 to 1. So there is a mapping which is done here, right? We are using a mapping function to map minus infinity to plus infinity to 0 and 1. Right? So which is this mapping function? The mapping function is nothing but sigmoidal function. So what is the job of sigmoidal function? To map the values from minus infinity to plus infinity to 0 and 1. That's the job of sigmoidal function. So the core of mapping function is nothing but your sigmoidal function. So it is nothing but a S-shaped function which will yield a value between 0 and 1. It is also called as logit function. So mathematically the logit function is logit of x is equal to 1 by 1 plus e power of minus x, nothing but the same sigmoidal equation which I gave in the previous slide. Here x is the independent variable, e is the Euler number, and finally logit of x is nothing but your sigmoidal function. Now, linear regression can result in very high numbers. We have seen that, right? In the previous sessions, linear regression, it will have very high numbers. Now, the same thing, I'm going to map it to the range of 0 to 1. So, that's the difference between linear regression and logistic regression. In linear regression, the numbers can be very high. But in logistic regression or sigmoidal function, remember, the values will range only between 0 to 1. So how do you do this? Using the logit function or the log odd function. So this is the logit function. So what is the odd? Odd is nothing but ratio of probability of an event occurring divided by probability of an event non-occurring or not happening. So that is p divided by 1 minus p. So log of p of x divided by 1 minus p of x is nothing but a0 plus a1x. So this we call it as log odds. Okay, so it is the log of probability of event occurring divided by the probability of an event not occurring. So log is nothing, this is nothing but the logit function or the log odds function. So now we have to solve for p of x. Okay, now we have the logit function, solve for p of x. So how do you solve for p of x is, you take the inverse. See, this is my log, I have to find p of x, take the inverse. So if I take the anti-log, I will get p of x is equal to exponent of a0 plus a1x divided by 1 plus exponent of a0 plus a1x. Now we know that sigmoid function will have a range from 0 to 1. So what we are doing is divide both numerator and denominator by exponent of a0 plus a1x. So when I divide, I get p of x is equal to 1 by 1 plus exponent of minus a0 minus a1x. Now rearrange this. What you can do is take this minus outside. So when you take minus outside, you get p of x is equal to 1 by 1 plus exponent of minus of a0 plus a1x. So basically here x is nothing but your predictor variable, e is the Euler number, and a are nothing but the regression coefficients. So finally you can say y is 1 if the probability or p of x is greater than or equal to 0.5, y is 0 otherwise. Okay, so this is the final thing. So basically this final equation denotes that how we have done mapping from real values to values in the range of 0 to 1 using the concept of probability. Now let's understand another function called as MLE, that is a maximum likelihood estimate function. So basically this function is used to determine the relationship between dependent and independent variables. So the goal of MLE is to learn values of parameters of the logistic model by minimizing the error in probability predicted by the model. So the goal here is to learn the values of the parameters. So optimal values of parameters obtained using MLE function is nothing but the set of coefficients. So this is the equation for your maximum likelihood estimate. So here this pi is nothing but the success of outcome and 1 minus is nothing but the failure of outcome. So this is your likelihood function. So it is the product of sums of success of outcome divided by failures of outcome to the power of yi into 1 minus pi I, which is the success, which is this whole thing is nothing but failures of outcome. So this is your likelihood function. Now let's see what are the different types of logistic regression. There are three types. Binomial logistic regression, where you just have two possible types of dependent variables. So you only have two possible types of dependent variables, either pass or fail. I'm talking about dependent variable, that is the output variable or the y variable. Multinomial means where you can have three or more possible types of dependent variables. I can say that the output is a class, or it belongs to the class dogs, or it belongs to the class sheep. So you can have more than two classes. That is called as multinomial. And the third one is ordinal. In ordinal, you have ordered types of dependent variables. You have a ordering between your variables like low, medium or high. So ordinal, as the word itself says, you're ordering. You have kind of an order between your output variables or dependent variables, whether it belongs to class low, class medium or class high. So now let's see the advantages of logistic regression. Now logistic regression is widely suitable for binary classification. It can also be extended for multiple classes. So if it is a multinomial logistic regression, as we saw in the previous slide, you can have multiple classes predicted. Now the disadvantages are, if you are using multinomial logistic regression where I can predict many classes, it still cannot handle many attributes. It can only handle linear features. Though I say it is multinomial logistic regression, it is only working for linear features. And the second one is, it does not work effectively if the features have multi-collinearity. In the sense, in logistic regression, the features should not be very much collinear with each other. Right? The assumption is the input features are not collinear with each other. If they are collinear with each other, then the results are not very effective. So that's it about today's session. In the next session, we will see problems with respect to logistic regression. Thank you so much.